Hello students, welcome to today's lecture of Theory of Machines. Today we are going to continue our discussion on degrees of freedom. In the last lecture we saw the degrees of freedom of an unconstrained rigid body, and we discussed that an unconstrained rigid body in space can have 6 independent motions, out of which 3 are translation motion about 3 mutually perpendicular axes and 3 are rotational motions about these axes. And we define the degrees of freedom of an unconstrained rigid body in space as the number of relative motions that the body can have in space, right? In today's lecture, we are going to discuss the degrees of freedom of a kinematic pair. As we have learned that a kinematic pair is a connection between 2 links having relative motion between each other, and this motion should be a constrained motion. Now, this connection of a link with another imposes certain restraints or constraints on their relative motion, and these number of restraints can never be 0 or 6. If the number of restraints becomes 0, that means the joint is disconnect and it will no longer be a kinematic pair. Similarly, if the number of restraints becomes 6, that means the joint has become solid. So there will be no relative motion. So again, it will not be a kinematic pair, right? Now let us understand this statement that the connection of a link with another imposes certain constraints on the relative motion by some demonstrations. So here you can see a kinematic pair with one link as a plate in blue color and another link as a cube placed on the plate in grey color. So as you can see here that the bottom surface of the cube is in contact with the plate, and thus this is forming a joint. And this joint is actually imposing some constraints or restraints in the motion of the cube relative to the plate. As we have learned in the last lecture that an unconstrained body or a free body in space can have 6 independent motions, out of which 3 are the translatory motion in the x, y and z directions, and 3 are rotary motions about these axes. So let us see which motions are possible and which motions are restricted for this kinematic pair. If you see here that this cube can move in the x direction and also in the z direction, but there is no motion in the y direction, because if we lift the cube from the plate, then the connection will be broken and it will no longer be a kinematic pair. So the motion in y direction is restricted, right? Similarly, you can see that this cube cannot rotate about the x-axis. Similarly, it cannot rotate about the z-axis, but it is free to rotate about the y-axis, right? So from this demonstration, we can see that one of the translatory motion is restricted and 2 rotational motions are restricted. So there are total 3 restrictions, or there are total 3 restraints for this kinematic pair. So having seen this demonstration, we can define the degrees of freedom of a kinematic pair as the number of independent relative motions, both translational and rotational, a pair can have. Or mathematically, this can be written as degrees of freedom is equal to 6 minus number of restraints. 6 is the maximum number of motions that a free body can have, and the total number of restraints any connection is imposing on a kinematic pair will be subtracted from 6. That will give you the degrees of freedom of a kinematic pair. So these numbers of restraints that a link is imposing on another will depend upon the type of connection which exists between the 2 links. So for the example which we just saw of a cube on plate, what are the number of restraints that we saw for this kinematic pair? First, the motion in y direction is restrained. This was the translation motion in y direction that was restricted. Also, rotational motion about x-axis was restricted, And similarly, rotational motion about z-axis was also restricted. So there were 3 restraints for this pair. So for this pair, the degrees of freedom would be 6 minus 3. That is equal to 3. So it will be having 3 independent motions: translation motion in x and z direction and rotational motion about y-axis. Right? So the degree of freedom is defined as the number of independent relative motions that the kinematic pair can have, or it can be formalized as degree of freedom is equal to 6 minus number of restraints. Right? So let us now see some more examples where we can see how the type of joint is responsible for the number of restraints. So whatever independent relative motions a kinematic pair can have, that will be the degrees of freedom of that kinematic pair. So this is another kinematic pair in which a cylinder is placed over a plate. So there is a contact between the cylinder and the plate. So let us see which motions are possible and which will be restricted. So you can see that the cylinder can translate in the x direction. It can also translate in the z direction, but it cannot translate in the y direction, because if we try to lift the cylinder, then the connection will be broken and it will not be a kinematic pair anymore. Right? Similarly, you can see that cylinder can rotate about the x-axis, but there will be no rotation about the z-axis, and it is free to rotate about the y-axis. Right? So what we observe for this kinematic pair, that one of the translatory motion is restricted and one rotational motion is restricted. So in total, the number of restraints will be 2. So for cylinder on plate kinematic pair, the degree of freedom would be 6 minus 1 translation motion and minus 1 rotational motion. So these will be 2 restraints. So the degree of freedom would be 4. Right? Let us see one more example where the degree of freedom will be 4 and the number of restraints will be 2. So this is an example in which a sphere is placed inside a hollow cylinder, and so in this kinematic pair we can see that there will be no translatory motion along the x-axis because of the wall of the cylinder, but there will be motion in the z direction, that is along the axis of the cylinder, and there will be no translatory motion along the y-axis because of the wall of the cylinder. Also you can see that the sphere will be free to rotate about all the 3 axes. It is free to rotate about the x-axis, it can rotate about the y-axis, and it can also rotate about the z-axis. So we can see from this demonstration that there are 2 translation motions that are restricted. So for example of sphere inside a hollow cylinder, we have a degree of freedom as 6 minus 2 translatory motions which are restricted. So the degree of freedom will be 4. Right? Now let us see another example where there will be 3 restraints as we saw in the first example, and the degree of freedom will also be 3. So this is a spherical joint in which you can see that a solid sphere is placed inside the cavity of a coal, right? And you can see that there can be no translatory motion in either of the directions. There can be no translation motion in the x direction, there can be no translatory motion in the y, and also there can be no translatory motion in the z direction, right? But as you can see here, the sphere is free to rotate about the x-axis as well as about the y-axis and also about the z-axis, right? So in this demonstration, we can see that there are 3 restraints, and all the 3 restraints are for the translation motions. So the degree of freedom for the spherical sphere, which we have already studied when we studied about the classification of the kinematic pair. So for this, the degree of freedom would be 6 minus 3 translation motion. So it will be equal to 3, right? Now let us see another example in which the number of restraints would be 4 and the degree of freedom will be 2. So as you see in this figure, there is a kinematic pair in which one of the link is a cylindrical bar or a shaft which is placed inside a hollow cylinder. And notice one thing, that there are no collars or bearings here. So as we see here, the shaft will not have any translatory motion along the x-axis, and it will also not have any translatory motion along y-axis, and this is because of the walls of the hollow cylinder. But it will be free to translate about the z-axis, that is along the axis of the hollow cylinder, right? So two of the translatory motions are restricted and one translatory motion is possible. Also, as we can see here, that this shaft will not have any rotary motion about the x-axis, and also it will not have rotary motion about the y-axis because of the walls of the cylinder, but it will be free to rotate about the z-axis, that is the axis of the cylinder, right? So two rotational motion will also be restricted. So here the total number of restraints would be 4, 2 translatory motion and 2 rotational motions will be restricted, right? So the degree of freedom for this pair would be, for cylinder inside a hollow cylinder, the degree of freedom would be equal to 6 minus 2 translatory motion and minus 2 rotational motions. So the degree of freedom would be 2. So in this pair, the shaft will be free to rotate. Also, it will be free to translate about the axis of the hollow cylinder, right? So these are the two independent motions that are possible. Now let us move to another example where there will be 5 restraints and the degree of freedom would be 1. So you can see here there is a square bar which is placed inside a square hole in a cube. So this is a prismatic pair. So as this is a square bar and it is placed inside a square hole, so there will be no rotational motion that will be possible. This we can see just by observation, and it will only be able to slide along the axis of the square hole, right? So we can see here that this square bar will not have any translatory motion along the x-axis. Also, it will not have any translatory motion along the y-axis because of the walls of the cube, but it will only be free to slide along the z-axis, that is the axis of the hole. So this is the only translatory motion that is possible, and other 2 translatory motions are restricted. Also, it is shown here that there will be no rotational motion about any of the 3 axes, right? So all the rotational motion will be restricted and 2 of the translatory motion will be restricted. So total number of restraints is 5, right? So the degree of freedom for a square bar in a square hole, that is a prismatic pair, the degree of freedom would be 6 minus 2 translation motion and minus 3 rotational motion. So the degree of freedom would be 1, right? Let us now see another example which we also discussed during the classification of the kinematic pairs. Is a cylindrical shaft which is placed inside a hollow cylinder but with collars at both the ends or bearing at both the ends, right? So due to the collars, the sliding motion of the shaft will be restricted along the axis of the hollow cylinder. So as we can see that there will be no translatory motion in the x direction, there will be no translatory motion in the y direction. This is due to the walls of the cylinder, and there will also be no translatory motion along the axis of the hollow cylinder due to the collars, right? We can also see that due to the walls of the cylinder, the rotational motion about the x-axis and about the y-axis will be restricted. So this shaft will only have rotational motion along the z-axis, that is the axis of the hollow cylinder, right? So in total, 5 restraints will be there, 3 translation motion will be restricted and 2 rotational motions are restricted, right? So the degree of freedom for a cylinder inside a hollow cylinder with collars, so the degree of freedom would be 6 minus 3 translation motion are restricted and minus 2 rotational motion are restricted. So the degree of freedom would be 1, right? That is the rotary motion about the axis of the hollow cylinder will only be possible, right? Now let us see one example in which the degree of freedom would be 5 and the number of restraints would be 1, right? So here you see a kinematic pair in which a solid sphere is placed over a plate and there is a contact between the two, right? So as per our previous discussion, we can't lift the sphere because if we do so, then the contact will be broken and it will no longer be a kinematic pair, right? So as shown here, the sphere would be free to translate about the x-axis and also about the z-axis, but there will be no translation motion about the y-axis or in the vertical direction, right? So one of the translatory motion is restricted, and also as you can see here that the sphere would be free to rotate about all the three axes. That is, it is free to rotate about the x-axis, it is free to rotate about the y-axis and also about the z-axis, right? So all the three rotational motions are possible. So we see here from the demonstration that there will be total one restraint that will be imposed by this joint, right? That is, the vertical motion of the sphere is restricted. So for a sphere on plate kinematic pair, we see that the degree of freedom would be 6 minus 1 translatory motion is restricted. That is, the motion in the y direction is restricted. So the degree of freedom would be 5, right? So we have seen a lot of examples with various number of degrees of freedom. We started with the degrees of freedom of 6, which we saw in the last lecture. And today we saw the examples of degree of freedom of 5, that is the example of sphere on a plate. Then we saw the examples of degrees of freedom of 4, that is examples of cylinder on plate and the sphere inside a hollow cylinder. We also saw the example where the degree of freedom is 3, the example of spherical pair and the example of a cube on a plate. We also saw the example where the degree of freedom is 2. We saw the example of a cylinder inside a hollow cylinder, right? And we also have seen the examples where the degrees of freedom is 1. That is the example of the prismatic bar, that is a square bar which is placed inside the square hole in a cube. Also the example of cylinder inside a hollow cylinder with collar, right? These are just a few of the demonstrations, but there can be many more examples which you can observe in day-to-day life. So we just saw a few of the examples to make you understand the concept of degrees of freedom of a kinematic pair, right? So the degree of freedom of a kinematic pair will be the total number of independent relative motions, both translational and rotation, that a pair can have, right? So, and it is formulated as the degree of freedom of a kinematic pair is equal to 6 minus number of restraints, right? So I hope the degree of freedom for the kinematic pair is understood, right? And this is how, depending on the type of the joint between the two links of the kinematic pairs, the number of restraints and the degree of freedom is decided, or the number of independent relative motions that the kinematic pair can have can be known, right? So I hope you have understood the concept of degrees of freedom of a kinematic pair. So that is all for today. Thank you very much.